So welcome back everyone, and in this chapter I will demonstrate the novel catalysis that we utilize in the Nefertiti program. And previously, the promoted rhodium-based catalysts embedded in carbon nanotubes stand out as one of the most prominent catalysts for Fischer-Tropsch synthesis towards CO2 oxygenates. And in the literature, it is reported that about 40% selectivity towards CO2 oxygenates are achieved under considerable carbon monoxide conversion. And the key for high oxygenate selectivity is due to the so-called confinement effect of the highly promoted dispersed rhodium particles ingredient with manganese, lithium, iron inside the carbon nanotube that promotes the CC coupling and the formation of C2 plus oxygenates. So in this work, we take advantage of this catalyst and we first try to replicate the literature, and the process include reflux, sonication and wet impregnation, as well as the controlled annealing. And these are very typical steps of how we prepare supported catalyst at lab scale. The first step is the reflux of the raw carbon nanotube with nitric acid. And the goal of the step is to create carbon nanotube with open end that allow growth of promoted rhodium particles inside the tube. And second, we sonicate and use the wet impregnation method. We prepare aqueous solutions and draw into the carbon nanotube channels by capillary force during the sonication so that the metal precursors can homogeneously distribute inside the carbon nanotube lumen along the tube axis. And later we dry the material and anneal the catalyst so that we turn the metal nitrate precursors into promoted rhodium-based particles. In heterogeneous catalysis, the activity assessments are always of key importance for catalyst development. And here we use GC, which is gas chromatography in the project. This is an analytic technique used to separate and quantify the chemical components of a sample mixture to determine their presence. The vaporized sample passes through the column that is carried along by a continuous flow of inert gas. So here we have the component of the sample include unreacted carbon monoxide, hydrogen, C2 oxygenates, which is vaporized, and some byproduct including methane and carbon dioxide pass through the column at different rates depending on their chemical and physical properties and the resulting interactions with the column filling, which is called the stationary phase. So in the spectrum, we can see that all different components can be well separated. We can see the oxygenated product include methanol, ethanol as the primary product, as well as other products include hydrocarbons. So in this picture, you can see that the prototype of our continuous plug flow reactor, that is combination of the first reactor, which use photocatalytic conversion of water and carbon dioxide into a mixture of carbon monoxide and hydrogen. We remove the oxygen through a membrane, and then the syngas is passed into the second plug flow reactor, which utilizes the xenon lights as the simulated light source to convert into C2 oxygenates that include ethanol. So the right-hand side picture showing the device that we utilize for catalyst assessments at Peking University. Over multiple attempts, we find out that the best photocatalytic Fischer-Tropsch synthesis catalyst can achieve about 50% selectivity towards oxygenates with about 3% carbon monoxide conversion. And after extensive calculation, we found out that higher than 60% reduction of the current cost of ethanol production can be achieved, with up to 50% higher energy conversion efficiency achieved due to the utilization of renewable sunlight as the energy input, with water and carbon dioxide as the feedstock. So catalyst characterization can provide us opportunities to understand why the catalyst gives certain activity or selectivity. The first technique we use is the X-ray diffraction. It is a versatile, non-destructive analytic tool used to analyze the physical properties such as phase composition, crystal structures, and orientation of powder, solids, and even liquid samples. So the figure demonstrates that in the XRD pattern of the prepared supported rhodium-based catalyst, display only the peak correspond to graphite carbon in the carbon nanotube, and peak corresponds to rhodium, as well as other promoters were not shown in the XRD pattern, which means they are highly dispersed with particle size less than 5 nanometers. So that's below the detection limit of the X-ray diffraction technique. Another technique we use is the UV-vis spectroscopy. It is an analytic technique that measures the amount of discrete wavelengths of UV or visible lights that are absorbed or transmitted through a sample in comparison to a reference or blank sample. So here we prepare the supported rhodium-based catalyst inside the carbon nanotube, as well as its counterpart, which is supported rhodium-based catalyst on a nanodiamond graphite. And both catalysts are black in nature, and they display strong absorption at 200 to 800 wave number region, demonstrating that they are capable of converting UV light, visible light, and infrared radiations, implying a high utilization efficiency of solar energy over the catalyst. And in conclusion, we prepare the promoted supported rhodium-based nanoparticles embedded in carbon nanotubes, and the best photocatalytic Fischer-Tropsch synthesis results over the catalyst achieved about 50% selectivity towards oxygenates with about 3% carbon monoxide conversion. The UV-vis spectra indicate that the catalyst display excellent absorption of UV light, visible light, and infrared radiations. The photocatalytic Fischer-Tropsch over the promoted rhodium-based catalyst can increase the density of reactants and hence create a local higher pressure favoring the C2 oxygenate production. And last but not least, we found this type of catalyst are facile to anchor, and that provides us opportunity to utilize it in a microflow reactor. And I believe in the next chapter, we'll focus on discussing the anchoring technique of this specific catalytic material inside the microfluid channel. And at the end, I would like to thank all the collaborators who make this research program running smoothly. And Again, I thank all of you for listening, and please leave your feedbacks in the comments. Thank you very much.